Okay, now it should work by now. This is the third lecture. Welcome everyone. We are going to consider it can be split into two parts. Namely, roughly speaking, random variables and all that stuff that's going on with them. I would, first off, I would basically consider to skip that part, but since I need to define it actually, at least from the practical perspective, I would consider expectation and variances and so on of random variables, both for discrete as well as continuous ones. And I will also consider basically both expectation and variance of transformations, especially linear transformations, which are the most common ones. I think you've seen this before, so I'm going to basically be quick on that. And as well as expectations and variances of sums later on. Okay, so again, because we're going to need that stuff. So this is basically also another issue. Now I'm going to look at uncorrelatedness and dependency. Uncorrelatedness or covariances are considered, and that is also necessary for considering variances of sums, by the way. So I'm going to give you an idea, but this is going to be the theoretical covariance and the theoretical correlation, so not the empirical one. So based on random variables, there is going to be pairwise and mutual independency, which is defined through the cumulative distribution functions. And we're going to look at i.i.d. random variables. i.i.d. means this is an acronym for independent and identically distributed. We're going to talk about that later on. I think basically you've seen this before previously, so again, but I wanted to have that actually considered. So we're going to look at expectations and variances of processes. And based on that, you would need to understand how this works when it comes to random variables, because what you do basically on random variables is going to be the same thing that you would need to do on stochastic processes. And yeah, so after that, this is going to be actually the second part. We're going to look at convergence of random variables. There is different types, so maybe you can, you can screenshot that if you like. So convergence and distribution, there is convergence in probability of random variables. There is going to be almost sure convergence. Okay, so these are the three major types. Then you have also convergence in mean, which is going to be relevant for stochastic processes also. Okay, and we're going to look at the specific case, which is a mean square convergence. This is a specific case of convergence in mean. And what's basically behind that. And as an examples, I have the central limit theorem. We're going to do some asymptotics. And based on that, you can simply just use the central limit theorem as well as the weak law of large numbers. There is both the weak and a strong version. We're going to consider both, but I'm going to focus on the weak one. And that's pretty much it. So again, this is the two parts. The first part is probably well known, as I assume, but probably not the second part. Anyway, let me check whether this works, but it looks legit, so all right, we're gonna continue. All right, guys, so that's pretty much it, what we're going to do today. Now, again, we're gonna look at a bunch of definitions, so maybe, again, these are the first part, Bill. You've probably seen them. So I'm not gonna waste some time on that. Last time we discussed properties of cumulative distribution functions, and this time I want to give you basically the idea how to, let's say, establish them when it comes to discrete as well as continuous random variables. Again, please recall that the cumulative distribution function of a random variable capital X at point small k is going to be corresponding to the probability that the random variable is not greater than small k. Okay, and again, we discussed that last time. We were defining it properly and so on. So when it comes to basically measures and this and that, but this time we're going to focus on basically the application. If X is discrete, then its realizations are going to be countable. So in that case, the cumulative distribution function at point k will correspond to the sum of its probability mass functions. Okay, so fx is going to be basically the probability mass function for which actually x is not greater than k. So again, x is supposed to be an index. I mean, when it comes to the sum notation, it's supposed to be like, okay, 0, 1, and 2, and so on. But again, without loss of generality, this notation is not very clean in that regard, but I don't want to have that too many indices and stuff. So again, the sum of all realizations for which the realization is not greater than k. That's pretty much it, okay? And then we're going to use basically the unconventional notation, okay, which is going to be simple. And when it comes to continuous random variables, and I assume that continuous random variables will have density functions. So technically, if I say continuous, it means actually absolutely continuous, because if, as you saw, a cumulative distribution function is absolutely continuous, then the density function exists, you know, so that's what you saw last time, but in this case, I use the term absolutely continuous and continuous when it comes to random variables synonymously. So when it comes to basically the cumulative distribution function at point k, this is going to be the integral of its density, okay? And then, of course, x is going to be the integrand and so forth, and the upper endpoint is going to be k, and the lower endpoint is going to be minus infinity in general. Even basically the density is 0, let's say, between a certain interval. It doesn't really matter. You always end up doing that. Now, keep in mind, guys, that the density function, or let's say the differential attached to it, is going to be the differential of the cumulative distribution function. But just for the record, the cumulative distribution function is not necessarily differentiable, okay? Because density functions, you know, I mean, again, so, I mean, let's say the cumulative distribution function looks like this, okay? For example, let's say the uniform distribution, whatever, could look like this, okay? Then it's not going to be differentiable. So keep that in mind when you basically consider that issue. Anyways, but long story short, this is just a side note here. I'm going to look at an application, okay? That's not going to be a major one, so it's not a representative one, but when it comes to, let's say, a discrete distribution, let's say you have a probability, you have a discrete random variable with realizations 1, the second realization should be 2, and the third realization should be 4, each with probability 0.5, 0.3, and 0.2 respectively. Now, some of the probabilities, of course, is equal to 1 this time. And that is also true for every discrete distribution there is. Okay, so I think you've seen this before. Let's say you want to, I mean, okay, this is corresponding to the probability mass function at point 1, at point 2, and at point 4 respectively, obviously speaking, right? Now, we're going to look at the cumulative distribution function at point, let's say 2.5. Now, 2.5 is not the realization of the random variable x, but it doesn't really matter. You can basically also tell what the probability is for, actually for the random variable not being greater than 2.5. And the probability for that is basically, I mean, you need to select the realizations for which this is true. This is true for 2 and 1, okay? So those are the realizations which are not greater than 2.5. So when it comes to the cumulative distribution function at point 2.5, you will simply just sum up the probability mass function at the realizations for which basically that are not greater than 2.5, and that's pretty much it. So that's going to be 0.7, by the way, as you saw. Okay, based on that definition, all right, so you can look at you select, or you would pre-select those realizations that are not greater than 2.5. And again, if you basically consider the probabilities for those which are not greater than 2.5, you have the probability mass function at point 1 and the probability mass function at point 2, because those are the two realizations for which this is true, right? And you sum up the corresponding probabilities, and that's going to be pretty much it. So, and that's what you would do. So you have basically the probability for 1 is going to be equal to 0.5 then, okay? And and then the probability for 2 is going to be 0.3. So, sorry, I said 0.7. It's going to be 0.8, of course, right? So that's going to be the cumulative distribution function at that point. Okay, I think everybody has seen this before. Okay, I assume that this is nothing new. And but I'm not going to basically waste your time on that any longer. Let's say you have a continuous random variable, for example, a standard normal random variable. Now, when it comes to the standard normal distribution, the density function of the standard normal distribution, usually denoted by phi, but not necessarily. You can call it basically f or something. It doesn't really matter. Phi at point x is going to be 1 by the square root of 2 times pi times e to the power of negative 1/2 times x squared, right? So that's basically the density function. I think everybody's seen this before. It looks like this, okay? So this is basically what the density function would be. And if you want to consider the cumulative distribution function, sorry, at a certain point, let's say at point k, that would correspond to the area of the density from minus infinity to k. That's also, I think, worth mentioning. Okay, so the cumulative distribution function of the standard normal distribution is denoted by capital phi in general, okay? I think you've seen this before. And usually it would correspond to the area of the density between minus infinity, in this case, and 1.96. Now the density of the standard normal distribution is here, okay? I mentioned that before. You take the integral of that between minus infinity and 1.96, and of course you calculated this integral with respect to x, so that would be the integrator, and what you're going to get is basically the cumulative distribution function at that point. Now, it can be shown that this function has no primitive, a closed form primitive function. You know what primitive function is, or antiderivative, okay? Antiderivative. The German term is Stammfunktion, that's the German term, all right? So it can be shown that it has no closed form solution for its antiderivative, okay, which is true. So you have to calculate this integral numerically. Now, if you do something like this, again, you don't need to because there is a distribution table, so I think everybody's seen them. The cumulative distribution function of the standard normal distribution, okay, can be looked up, and let's say at point 1.96, you would go to row where 1.9 is, and then you would have 0.06 because 1.9 plus 0.06 is 1.96 after all, and where basically the row intercepts with the column, you will have the corresponding probability, which is a probability, by the way, 0.975, so 97.5%, roughly speaking, is going to be the probability that the standard normal distribution will not be greater than 1.96. So if you randomly select a sample from a standard normal population, you would find that the probability of selecting a value which is not greater than 1.96 would be, roughly speaking, 0.975 or 97.5%. All right? So, but that would be basically the value of this integral. Okay, so if you basically did this numerically, which you would not need to, okay, so we will not consider numerical integrations, but that's basically how you would end up with. And that's basically what I'm mentioning. Okay, so when you look at basically the diagram here, this is the density of the of the standard normal distribution. 1.96 is over here, and you look at basically the area on between minus infinity and 1.96, which would correspond to, and let me stress this because that should be important, this area would correspond to the cumulative distribution function denoted by phi of the standard normal distribution at point 1.96. Okay, so because that is the probability that the standard normal distribution would not be greater than that, namely not be greater than 1.96. Okay, I think everybody has seen that before. All right, so I hope this is not new. I mean, if it is, all right, then okay. So that would be the area left to 1.96, of course. Now, in this case, though, and that's also something which mentioning, if actually the cumulative distribution function at point 1.96 is going to be 97.5, which means that the probability that the standard normal distribution will not be greater than 1.96 is going to be, let's say, roughly speaking, 97.5%. Then you can call this value 1.96 to be the 97.5% quantile of the standard normal distribution. I think you have seen that one also, right? If the 97.5% quantile of a distribution is considered, that's going to be by definition a value which is not exceeded by 97.5% of that distribution. So since basically the standard normal distribution does not exceed 1.96 with 97.5% probability, 1.96 will be considered to be the 97.5% quantile of the standard normal distribution. Understand that point, guys? Okay, so that's basically telling you what you need to put into the cumulative distribution the cumulative distribution function, to get 97.5% out. And here on this side, okay, it will tell you what you get out, namely 97.5%, if you put 1.967 into it, okay? So that's basically what you have, all right? So you can call it the image, and that would be actually considered to be the pre-image. We talked about pre-images. I think, you know, that was the first lecture or something when I was introducing to that, okay? So let me summarize what this is about. So the cumulative distribution function at point 1.96 is going to be approximately, and that's basically what you end up with, 0.975, okay? So in this case, though, This means, on the other hand, since this function is, again, I mean, it's not bijective, but you can basically invert it. The density is not bijective, but the cumulative distribution function is the pre-image. Okay, so then this is basically what the pre-image of 0.975 of the cumulative distribution function is going to be approximately 1.96. Because 1.96 is going to be the 97.5% quantile of the distribution. Understand that point, guys? Okay, so what I think you've seen this before. All right, the cumulative distribution function of the standard normal distribution is a bijective one, so it's invertible in that case. Not every distribution does that, but the cumulative distribution function of the standard normal distribution is fulfilling that. Okay, it's strictly increasing, by the way. The density is not, but the cumulative distribution function is. That's not the cumulative distribution function. That's a density, guys. So those are two different things. All right, so do not basically confuse the two. Anyway, we're going to look at expectations again. So expectations and, well, variance and so forth. Now you will not need to use that basically based on distributions. Okay, so you will not need to calculate expectations and variances from given probability distributions. But you need to know how these things are, okay, and what properties do they have. And of course, I would need to give you a more or less proper definition on that. So if the random variable is discrete, okay, that's not the definition. I don't want to go basically too deep regarding the theory, because then you would need to consider Lebesgue measures, which I don't want to introduce here, okay, although it might be important, but that will be maybe, let's say, in a second part of this course. The expectation of a random variable, okay, if the random variable is discrete, is going to be its weighted sum of its realizations, okay, weighted by the corresponding probability. So keep in mind, guys, f is the probability mass function of the random variable, okay? F at point small x is the probability mass function at point small x. And if x is the realization, which is supposed to be, okay, then you will consider the expectation of a random variable to be the weighted sum of its realizations, each, of course, weighted by its corresponding probability. That's pretty much it, okay? Now, when it comes to continuous distributions, and, you know, I mean, let's assume that you have a density function. The sum is going to be basically changed by an integral, and actually the probability mass function is, I mean, it's not the same thing, so please keep that in mind, that the probability mass function is not the same as the probability density function, although I'm not distinguishing basically between the two when it comes to notation. I don't want to introduce too many variables, of course. So if x is discrete, then f is going to be its probability mass function, and if x is continuous, and it has a density, let's say, then f is going to be its probability density function. Okay, but the structure of this is actually going to be the same as that one. Okay, so basically when it comes to that, and I don't want to go into that, but this is basically what it would do. And I think you have seen that done before as well. First of all, I was basically considering, I would introduce Lebesgue measures and so on, but I decided not to. I want to focus on basically on stochastic processes instead. Okay, so this is something that you will not need, okay, because I will not let you calculate actually, I mean, maybe with a few exceptions or so, but we will not need to calculate expectations, neither expectations nor variances from given probability distributions. I think you've done that before, so you will not need to do it again. But I need to recall what it was. Okay, now the variance is itself an expectation. Keep in mind the variance is the expected squared deviation of the realizations of the random variable to its mean. Okay, so you're going to look at the deviation of the random variable, let's say the realizations of them, to its mean. So you need to calculate the mean first. Then you would need to take the square of that, and then you would have the expected squared deviation of the random variable to its mean being equal to the variance of the random variable. I think you've seen that one also before. Now, when you use basically certain properties of expectations, which I'm going to introduce you to, namely, and roughly speaking, actually the expectations of linear transformations in particular, you'll find that the expectation of the squared distances is going to be the expectation of the squares minus the square of the expectations. So for the variance itself, you would need to look at basically how expectations are considered. Okay, so the mean of the squares minus the square of the mean. roughly speaking, will also be equal to the variance. Now keep in mind, guys, that the variance is not negative, of course, right? Distances cannot be negative, I mean, especially when you're squaring them, right? So squared distances cannot be negative, and their expectations neither. If the variance of a random variable is 0, then the variance is going to be a constant. Maybe I should basically say that. Okay, so let's say if the variance of the random variable is 0, then this implies that the random variable is not random. Okay, it's going to be a constant. All right, so that should be clear now. And this is also true the other way around, by the way. So if, let's say, a random variable degenerates to a constant because there is no randomness anymore, then it has 0 variance, of course. Anyways, guys, okay, so the standard deviation, of course, is going to be the square root of the variance. I think this is also something which you're familiar with. And yeah, so again, I wanted to have that just considered because, again, as I said before, you need to know what it is, at least from the practical perspective, and not from the theoretical one. So that's not a theoretical definition, by the way. But we're going to look at some properties. For example, if x is discrete, how would you calculate the variance? When it comes to that, now the variance is going to be, as I said before, the mean of the squares minus the square of the mean. Okay, so it's just focusing on that. And the mean of the squares, on the other hand, which is here, so this expression is going to be, again, the mean of the squares, is the weighted sum of the squared realizations, each weighted by the corresponding probability. Keep in mind that the probabilities, which denoted here, are not going to be squared. Only the realizations, but not the probabilities. So the probabilities will not change, okay, although you transfer the random variable. I'm going to talk about transformations later on, just in a minute, okay, but that's basically how it will be, okay, and this is how you would calculate the variance of a random variable. I'm going to do that for a discrete case, okay, so just don't worry if you're not sure what this means. If x is continuous, then you would need to simply replace the sum by the integral, okay, and then the probability mass function by the density function, and let's assume that it exists, okay, so we're going to basically call the random variable actually continuous if its cumulative distribution function is absolutely continuous, because then it is made sure that its random variable, then its density would exist, all right, without loss of generality, of course. There is lots of weird distributions out there which have continuous cumulative distribution functions, but don't have densities. One of them is a Cantor distribution, but from a practical perspective, you can simply ignore them, okay? So this is just a distribution which contradicts to a lot of basically well-established misconceptions, by the way. But anyway, okay, I don't want to go into that. Now, regarding the expectation of a discrete random variable, I want to consider the example again with the previous probability mass function. I told you before, the mean / expectation, so both terms are used, the expectation of a discrete random variable is going to be equal to its weighted sum of its realizations, each weighted by its corresponding probability. So one is basically a realization of the random variable. How do you know? Because its probability is positive, of course, and it's going to be a realization of the random variable. So 1 times its probability plus the second realization times its probability plus the last realization times its probability. Okay, that's the last. So this is basically what you end up with. And then you would basically come up with the result that the expectation of this random variable is going to be 1.9. This is the weighted sum of its realizations, each weighted by the corresponding probability. I think you've seen this before, right? It's relatively easy. I'm not going to do integral calculus today because that is going to be just a subject of maybe next or upcoming lectures. Now, regarding the variance of a continuous one, again, I'm going to use the formula mean of the squares minus the square of the mean. Usually it's not the same thing, because if that were equal, then basically the variance, I mean, you would have 0 variance, of course, and that's not going to be working. Now, when it comes to a random variable, because then it would not be a random variable, so this is going to be, again, the mean of the squares is the sum of the squared realizations, or the weighted sum of the squared realizations, each weighted by its corresponding probability. So this is the mean of the squares, as you see, okay? And the mean of the squares minus the square of the mean. Now, the square of the mean was 1.9, so the square of the mean would be actually equal to 1.96 squared. Sorry, this is basically how this works. So you have that basically outside. Keep in mind, guys, the mean of the squares is not the square of the mean in general, because among others, the sum of squares is not the square of the sum. Okay, you know this from the binomial formula among others. Anyway, okay, so here in this case, it's going to be 1.29, which is the variance of this random variable, and the standard deviation is going to be the square root of that. Okay, so I think you've seen this before in an undergraduate course, but I wanted to have that recall. All right, okay, now looking at basically expectations, okay, when it comes to, for example, continuous random variables, looking at, for example, the standard normal distribution, which I talked about before. It has a density 1 by 2 times pi, 1 by the square root of 2 times pi, sorry, times e to the power of negative 1/2 times x squared. So the expectation is going to be the integral, okay, on its whole domain, usually, all right, so the domain of the normal distribution, or you can call it the codomain actually, is actually from the set of real numbers in general. This is going to be x times the density of the standard normal distribution, which is integrated with respect to x. Now, in this case, this integral can be written as a closed form. I mean, it can have a closed form solution, which is actually equal to 0. You find that one. So this is, I mean, done by integration by parts, which I'm not going to do it here. Okay, so this function has a closed form primitive function, by the way, which the density does not. Okay, so in this case, you would not need to solve this numerically. Anyway, if you do integration by parts, you'll find that this integral is going to be 0 after all. And that's going to be the mean of the standard normal distribution. What a surprise. I mean, the mean of the standard normal distribution, as you might know, is already 0. But this is just basically confirming it. And the variance is going to be equal to 1. Now, looking at the variance, again, the variance is the mean of the squares minus the square of the mean. And keep in mind, the mean of the squares is going to be calculated from x squared times the density. Okay, so looking at basically on this integral, this is the mean of the squares, and then you subtract the square of the mean. Now, the mean is 0, so its square is also going to be 0. So that integral is going to be equal to 1 after all. All right, so that's basically what you have. So when you do this, again, I'm not going to, so you can practice if you like. Integration by parts is going to be, or would be, an issue. You'll find that this integral is going to be equal to 1, but you don't need to do it now. So, okay. All right. So these are things that you've probably seen before. I just wanted to have recalled. You will not need to do this in the exam. So I'm not going to give you like probability distributions and, you know, giving you these kind of integrals, but this is going to be important. So expectation of variances of linear transformations in particular. All right. But every other transformation is also going to be an issue. What is a linear transformation of a random variable? A linear transformation is a random variable is a transformation of this sort. Okay, so you have an additive constant and you have a multiplicative constant. And what you need to know, among others, is that the expectation of a linear transformation is going to be the linear transformation of the expectation. So all you would need to do in order to address that is to calculate basically the expectation of x, because if you have the expectation of x, then you also have the expectation of its linear transformation by looking at basically the linear transformation of its expectation, right? So, I mean, if everybody doubles their income, the average income is also going to double. And if everybody increases his or her income by, let's say, 50,000 a year or so, then the average income is going to be basically increased by 50,000. So it's not a surprise, actually, that this is true. You could confirm this relatively easily when you look at the definitions that I just gave you, all right? Now, anyway, what the variance of a linear transformation is going to be, that's different. Because keep in mind, the variance is the mean of the squared deviation of the random variable to its mean. Okay, and that's going to be different. Now, it doesn't depend on the additive constant. So that's something which is need to be looked at. Okay, so the variance is not going to change if you add something to the random variable. And the question is why? I mean, of course, you could prove it relatively easily, but the intuition behind it is this. If you increase every realization of the random variable by a, let's say, then the mean is going to be increased also by a, and the distance between the new mean and the new realization will stay the same. So it's not going to change, okay? All right, and that's basically what you'll have, okay? If everybody increases their income by, say, 50,000, then the distance between your new income and the new average income will be the same. And that's why it doesn't depend on the additive constant. However, it will depend on the multiplicative constant, and it's going to be basically depending on its square. And the question is why? I mean, okay, you could prove it relatively easily when you look at certain properties of variances and expectations and so forth. It's easy to actually to show this because the variance is nothing but the expectation of the squared distance, all right, of the random variable to its mean. And if you multiply, let's say, the random variable by 2, then the square of the distance is going to be between the new mean and the new realizations is going to be actually 4 times as large, because that 4 is going to be the square of 2. All right, so that's basically the issue why it's depending on the square of the multiplicative constant times the old variance would give you that. Okay, so if you want to get rid of basically the multiplicative constant from the variance separator, so you want to take it out from the variance separator, you would need to square it. Please keep that in mind when you're looking at variances and so forth. And we're going to look at variances of stochastic processes, and you would need to have that. So I wanted to make sure that at least this is going to be considered. Now, when it comes to general transformations, again, one of them could be the linear transformation. That is a specific case for the general transformation. For example, the square could be another one. Okay? How would you basically, again, so I'm going to give you examples if you're not sure what this means. When it comes to the general transformation, okay, I'm going to distinguish between the two cases which are actually relevant in practice. So in practice, you have either discrete or continuous random variables, but in theory, don't forget that you can have actually 3 categories, which, I mean, there is a third category, which is neither, but I'm not going to consider that one. You have actually, I mean, when it comes to the expectations, okay, I mean, without the transformation first, okay, so let's forget about that. Okay, there is no transformation. First, the expectation of a discrete random variable would be equal to the weighted sum of its realizations, each weighted by its corresponding probability. Now, when you do a transformation of a specific sort, let's say, on the random variable, all you would need to do is just to apply that transformation on the realizations of the random variable, and that's it. And keep in mind the probabilities will not change. Okay, that can be also shown. And yeah, so that's basically what you have. Okay, and that's what I was collecting here. And that will be the same thing for continuous random variables. Keep in mind what you see down there. Okay, so this is not there yet because that's not true, not yet. Okay, this is the expectation of the random variable x. Now, when you do a transformation on basically of the random variable, all you would need to change is actually x to g of x, which would correspond to the expectation, okay? And the density will not be affected, okay? So that is important. So this is how you can bypass this issue, all right? So the densities, as well as the probability mass functions, don't change when you consider that. All you have to do is just transferring the realizations, and then you have the same weights, okay, because they're not going to change. Anyway, okay, so we're going to look at some examples, at least basically for the discrete case. I was not considering the continuous case. However, there was one which I was already addressing, namely the variance, because that was already a transformation, which was not a linear one, of course. Now, the expectation of, let's say, of x is the weighted sum of its realizations, each weighted by the corresponding realization, right? So that would be, again, this is not difficult to assess. 1 times its probability plus 2 times its probability plus 4 times its probability, because those are the realizations, right? And if you transfer or you consider basically their squares and you want to get the expectation of their squares, you would need to just square the realization. So that's going to be 1 squared times the probability plus 2 squared times its probability plus 4 squared times its probability, and that's that. This is the mean of the squares, by the way, right? We have seen that one before, and that is also basically applied accordingly. So the mean of the squares is applied accordingly. So that's going to be the mean of the squared realizations. Each realization, or each square, basically, is weighted by its corresponding probability. But or the realization actually, but it doesn't really matter. So you don't square the probabilities. I want you to basically aware of that. Now, that is also true for other transformations. So for example, you would consider maybe x cubed and the expectation of that, which can be done, for example, when calculating skewness or even higher moments. Okay, so that's the third moment, by the way. So that's called the third moment of the random variable. Okay. Okay. Yeah, so that is basically pretty much it now. Okay, wait a moment. I think somebody wants to enter. No? Okay. I put a do not disturb sign on the door. Okay, so if you see that, you could come in because you're participating, but if you don't, then I don't want to basically have the door opened every 5 to 10 minutes or so. Now, this is going to be actually the weighted sum of the cubes, right? Okay, so 1 cube plus times its probability, sorry, plus the other realization plus times its probability, and you know, these are the transformations. All right, is this clear? All right, so again, I don't really care what this would be. That's the third moment. This is how it's called. Or you would also calculate the fourth moment. That's going to be the weighted sum of all realizations taken to the fourth times their corresponding probabilities. So 1 to the fourth, I mean, that's equal to 1, but it doesn't really matter. 2 to the fourth plus times its probability plus 4 to the fourth, which is 56.5. Okay, so this is the fourth moment, guys. Okay, well, sometimes I will address the fourth moment of a random variable, at least for the discrete case. You know how to deal with that. Okay, when it comes to the standard normal distribution, you might remember that one. So again, let me add that to the consideration because again, I didn't do it here. But when it comes to, let's say, a standard normal random variable, so which is not a discrete one, of course, right? So when it comes to the standard normal random variable, we were collecting it. So the first moment of that was 0. The second moment was equal to 1. Okay, I mean, that corresponds to its variance because the mean of the squares minus the square of the mean is the variance in this case. The third moment, does anyone know what it is? The third moment of the standard normal distribution corresponding to the skewness is 0. That's also true, right? That would be 0. And the fourth moment of the standard normal distribution, based on the transformation theorem, okay, when you would try to address it, is equal to 3. All right, so you might basically be, I'm kind of wondering that you haven't seen this before. Okay, what the hell are you doing in finance when testing basically for normality of, let's say, asset returns? You would need to, I mean, you're testing whether the skewness and the skewness of the distribution of the returns is 0 and the kurtosis is equal to 3. Okay, because that would correspond to the normal distribution. Yes? Pardon? Like there's a test to... Yes, the Jacques-Barra test. That's the test what I'm talking about, okay? So when you do financial market models and you want to make sure basically that the sample is, let's say, consistent with the normal distribution, you're testing that, okay? Basically the third and the fourth moment. Anyway, I just wanted to, this is just a side note, so you would not need to do it, but that's basically worth mentioning. So when you Google, let's say, the standard normal distribution, you'll find it there. And it's also true for the logarithm, by the way. So the expectation of the logarithm, okay, is not going to be the logarithm of the expectation, by the way. So that's going to be actually the logarithm of 2 to the power of 0.47 if you do that. Okay, so this is the weighted sum of the logarithms. Anyway, I just wanted to have that mentioned here. But that's the principle that is applied and that is also actually consistent with the applications regarding continuous random variables, which I'm not going to do. So I was only considering the discrete ones, not the continuous ones. Okay? Now, what are the properties based on expectations? I also need to address what expectations or how expectations are calculated of products. This is, again, the expectation of a discrete random variable, which is corresponding to its weighted sum of its realizations. So those are the realizations of the random variable, and you weight them by the corresponding probabilities. There's nothing new, so the weighted sum is going to be that. Now, if you consider expectation of products, okay? So let's say you have an expectation of x times y, you need to have the so-called joint probability mass function. So you need to put it in short terms, you need to have the joint distribution, okay? When it comes to when it comes to discrete distributions, the joint distribution is represented actually by the contingency table, right? So you've probably seen that one, okay? So here you have the realizations of x, okay? Here, let's say you have the realizations of y, and inside the contingency table, you can call it contingency table, you have the so-called probabilities referring to their joint distribution, okay? And that's where you basically take those from, okay? So those are basically the probabilities. It looks much more difficult than it really is. And then you would need to have basically the weighted sum of the products based on this joint distribution, okay? So let's say if x has 2 realizations and y has 3 realizations, then the contingency table is going to be a 2 by 3 matrix. And so there you have 6 summands based on that. So the weighted sum of the products is going to be you have those 6 realizations which are generated from the combination of the two. Okay, so the realizations of the product will be the number of realizations in general is going to be equal to the product, to the product of the number of realizations of each. Okay, so if x has 2 realizations and y has 3, then the product will have 6, and that should be clear. And so you have 6 different probabilities in general, and they are taken from the joint distribution. I think you have done this before. I didn't do it, so I was not basically applying it here because I wanted to do something else. I don't want to do basically the whole, let's say, repetition of your undergraduate courses. But I just wanted to have mentioned that. So basically, and the same thing is done when the random variables are continuous. Okay? So when they are continuous, the expectation of the product will be equal to, you have the double integral of the products basically based on the joint density function of the two, okay, which is a theoretical concept, by the way. So for the normal distribution, it's relatively easy, but for most other continuous distribution, it's not that easy to represent this. Anyway, I think you also seen that one, okay, as again, I basically recall it, but I'm not going to elaborate on that anymore. So based on that, okay, you could calculate the covariance. The covariance is actually the mean of the product of the deviations of the random variables or the respective mean. So this is the deviation of x to its mean, and the other factor is going to be the deviation of y to its mean. And if you basically take the product of the two and calculate the mean of the product of the deviations, you'll find that this is going to be the covariance. This is going to give you basically this is going to be a measure for the linear relationship between the two random variables. This is more, let's say, not very practical in this issue, so more practical would be considering the mean of the products minus the product of the means, which is actually here. So basically, based on the same principle as the variance, this is basically how you end up with. And the reason why I introduced the mean of the products was because, yeah, it is part of the covariance of two random variables. Okay, so when you look at basically the covariance of, let's say, 2 stochastic processes, you would need to have actually their joint distribution to get that, because you would need to have the expectation of the products. For the means of each respective ones, you don't need the joint distributions, you just need the marginal distributions, but the expectation of the products, you do need that. Okay, so the mean of the products minus the product of the means, that's going to yield the covariance in general. Okay, now again, I'm not going to let you calculate the covariance based on probability distributions. So that's not going to be an issue. But you would need to basically consider, let's say, properties. Now, x and y are considered to be uncorrelated if their covariance is 0, okay? Which means that there is no linear relationship between them. But keep in mind, guys, just because there is no linear relationship between them, which means that they are uncorrelated, it does not imply that they are independent. Okay, if they're independent, then they are uncorrelated,
but just because they're uncorrelated, they're not necessarily independent. Independency is going to be that there is no relationship between them at all, and uncorrelatedness means that there is no linear relationship. If there is no relationship between them at all, then there is no linear relationship, but just because there is no linear relationship between them, there is no relationship between them. That doesn't necessarily mean that there is no relationship between them at all. You understand the point? Okay, but the most common relationship is the linear one. So if there is a relationship between two random variables or two samples of some sort, whatever, most of the time it's going to be the linear one. However, this is not necessarily true. Anyway, so that's something which I want to mention. I'm going to look at some properties, for example, based on linear transformations. So how would you consider covariances, a covariance of linear transformations? Now, again, keep in mind both variables are subject to a linear transformation respectively. And what I basically worth mentioning is that the linear transformation, or the covariance of the linear transformations, does not depend on additive constants. It only depends on the multiplicative ones, but it will not depend on the additive constants. When you look at the mean of the products minus the product of the means, you can confirm that relatively easily. Okay, additive constants, I mean, when you look at distances of random variables to their means, or realizations to their means, and you basically increase them by a, you'll find, for example, for x, you'll find that the mean is also going to be increased by a. So the distance between the new realization and the new mean will be the same. And that's the reason why the covariance does not depend on these additive constants, because the covariance is the expectation of the product of the distances between each random variable to its respective mean. And that's basically what it is. Okay? And if you increase the random variables by a constant, then the distance between the new realizations and the new mean will not change. That should be clear. All right? But you have dependency based on the multiplicative ones. And if I say multiplicative, this is basically applied on the random variable. Okay? So if you basically double one and the other is going to be triple, then the covariance is going to be 6 times as large as the previous one. Okay? Anyways, that should be clear. Now, based on that, there is a correlation. Correlation on theoretical basis is the covariance divided by the product of the standard deviations. So that's the standard deviation of the first, and that's going to be the standard deviation of the second. It's not a surprise. Okay, I think you've seen this before. Okay, it's not a big deal. Anyway, okay, so notice that the correlation, and that can be shown relatively easily, is always between -1 and 1. If it's equal to 1, then this means that x is a linear transformation of y, and a positive linear transformation, meaning that there is a positive relationship between y. So let's say if the correlation is equal to 1, then this implies that y is, of course, a linear transformation of x, where actually the multiplicative constant is greater than 0, right? Because the relationship is perfect. So that's going to be a perfect, one is a linear transform of the other. And if the correlation is negative, in particular -1, then you'll find that the multiplicative constant, then still y is going to be a linear transformation of x, but then the multiplicative constant, this one is going to be negative then. But it doesn't really matter. Now, if x is a linear transformation of y, then y is also going to be a linear transformation of x. If you are married to someone, that person is also married to you, so that is a one-to-one relationship, okay? So if y is a linear transformation of x, then x must be also a linear transformation of y, okay? Now, I'm not going to talk about that because we're going to address sometimes maybe correlations, okay, when you look at multivariate processes, but I want to focus on, let's say, single-dimensional ones instead. So again, random variables, let's say you have x and y, are called pairwisely independent, and that's going to be the new concept, if the joint cumulative density function, the joint cumulative density function, and I haven't said this, but I wanted to stress this, is going to be calculated from the double integral of the corresponding joint density if it's a constant, or the double sum if they're the joint probability mass function, by the way, okay? Now, this is going to be the product of the marginal densities. If the joint cumulative distribution function of two random variables equals to the product of the margin, sorry, not the densities, the marginal cumulative distribution functions, respectively, then they're called pairwisely independent. Now, this is not a very practical concept because most of the time, even the processes you are specified, joint cumulative distribution functions are hard to get, okay? So the marginal ones, maybe, but marginal distributions, maybe, but not specifically the joint distributions. It's very hard to basically establish that one. So it's not a very practical concept, by the way. But anyway, I would need to define it. And of course, pairwise independent, otherwise if it's not true, okay? Now, again, I was explaining this here, the joint cumulative distribution function, okay? This is it. This is the joint cumulative distribution function, is equal to the probability at point x and y that capital X, which is a random variable, is not greater than small x, and capital Y is not greater than small y. And so this sign here in the middle, okay, the comma, let me just stress that, okay, so the comma here, that one, okay, means and. Okay, so this means that that is true and the other is also true, both, okay? So that's some sort of a joint probability. Again, it's not a practical concept, to be honest. But anyway, there's no other way to do it. Now, of course, these are the marginal distributions. You saw basically cumulative distribution functions of random variables already, so we don't need to consider them again. Okay, and if the product of these two is equal to that, then they are called pairwise independent and pairwise independent otherwise. Now, again, this is not a practical concept, to be honest, because again, joint among others, again, I mean, the marginals are also going to be hard to get, but the joints even more. Okay, so, but again, I will need to consider that anyway, you have mutual independency if that is also the case for a multiple random variables or a set of multiple random variables. Also, now this is even more difficult, okay? So if you have even more than two, getting the cumulative distribution function of, let's say, a higher dimensional random variable, so you can call it the random vector here. That would be basically it. This would be, if this is equal to the product of its marginal cumulative distribution functions, then the random variable is called mutually dependent. Okay, now here you see again the cumulative distribution functions and the joint cumulative distribution function. That's a joint version, and these are the marginal ones, okay? And those are the marginal ones. The light blue are the marginal ones. Okay, all right. I hope this is clear now. Let me check. Okay, good. Now let's continue. So I'm gonna basically address the relationship between the two. Of course, if they're mutually dependent, they're also going to be pairwise independent. That is also true. I mean, if all of them are independent, they're all going to be independent if you basically just grab two of them, okay? So those two are going to be independent all the time, but basically the converse is not true in general. So just because they're pairwisely dependent, let's say, they're not going to be dependent, not necessarily going to be, the other way around, sorry. Just because they're pairwisely independent, they're not going to be necessarily dependent in general, okay? Most of the time it is, but not in general. So you cannot reverse the issue. So those two are not equivalent, basically. Okay, so pairwise independency does not imply mutual. And yeah, but if they're mutually independent, they are also pairwisely independent. That's for sure. Anyways, I just wanted to have that mentioned. And there is another remark here. If they're independent, so if independence is true, which means that they're, and okay, so if there are just two of them, okay, they are of course mutually, both mutually as well as pairwisely, okay, if just two of them. So just simply say independent. If they're independent, which means that their joint cumulative distribution function is equal to the product of the marginal distribution function, then this is also true basically regardless of their discrete or continuous with the joint / marginal densities. Okay, so if both are continuous, then you have the joint density, and if both are discrete, then you have the joint probability mass function, right? Okay, so the joint probability mass function. That is also going to be true, okay? So if they're basically in discrete case. Now, this is also true in the other way around. So when it comes to discrete random variables, and you'll find, let's say, hypothetically, that they joint probability mass function is corresponding to their product, to the product of their marginal probability mass functions, or simply just call them probability mass functions, respectively, at every point there is, then you will have also independency, okay, when it comes to the discrete case. And that is also true for the continuous case, by the way. So when you look at densities. Okay, now, yeah, so that is basically the issue here. So those are actually the marginal densities or the marginal probability mass functions, whether they are dependent or discrete or continuous. Most of the time, they're both either discrete or both are continuous. Okay, if that is not true, then, okay, this is something which you would not need to consider. Now, I'm going to look at basically the other important definition. If they're identically distributed, this means that they have the same distribution. So let's say one is following the normal distribution, namely maybe the standard normal distribution, and you're absolutely sure that this is the case, then every other is going to be following the standard normal distribution also. Okay, so that means that they have identical distributions. You understand the point? Okay, if one is following, let's say, the binomial distribution, then every other is going to be also following the binomial distribution. That's what you would need to consider. All right? This means identically distributed. So they are having the same distribution, not necessarily a uniform distribution. They have the same distribution. Now, if this is the case, now then what? Okay, I mean, they said they have the identical distribution if their cumulative distribution functions are equal. Okay, because the cumulative distribution function, although it's not very practical, is well defining every distribution there is. And if they're equal at every single point, this means that their distributions are equal. So that means that they're identically distributed, by the way. And that's for sure. Okay, now you need to look at basically at single points, which are denoted by x. And if this is true across the board, they have the same distribution. This is how you say it. And if in addition, okay, there are also, in addition, independent, mutually, all right, mutually. So that comes in addition to that, okay, mutually, which means that the cumulative distribution function, the joint cumulative distribution function, is equal to the product of their marginal distribution, marginal cumulative distribution functions or cumulative distribution functions or respective ones. This is basically mutual independency, by the way. Then, of course, they're also pairwise independent, but that's not the point. We're going to use the following notation, i.i.d. i.i.d. is an acronym standing for independent, or independently, you can call it, but independent means basically referring to the random variable. So they are independent, and they are identically distributed. That's what it stands for. Okay, so I'm going to use that quite frequently. And if this is the case, so random variables are i.i.d., which means that random variables are i.i.d. Number one, they have the same distribution, each of them. And number two, they are independent, even mutually. Okay? And that's a very strong assumption, by the way. So, but that makes things a lot easier. Okay, if there are i.i.d., and let's say hypothetically there are, if there are i.i.d., then what? Okay, so then, of course, then they have the same distribution. But if they have the same distribution, they have the same moments. So the expectation of the first is going to be the expectation of every other. Otherwise, if that was not true, they would not have the same distribution. Okay? Now, the converse is not true either. So just because they have the same expectations, it doesn't necessarily mean that the distributions are equal. But if their distributions are equal, they have the same expectations, and they have the same variances also, respectively, right? So the variance of the first is going to be the variance of the second, is going to be the variance of the third, and is going to be the variance of the last. They're all equal, all right, respectively. It doesn't necessarily mean that the expectations are equal to their variances. No. Their respective expectations are equal, and their respective variances are equal if there are i.i.d., okay, which means that they have the same distribution, respectively, and they are independent. You understand the point? If this is the case, you must know their moments are equal. All right? Okay? So that's, I mean, actually this is clear, but I wanted to just basically clarify that. In this case, you can also write, since basically, let's say the expectation is mu, which is usually associated with the normal distribution, how necessary. They're not necessarily normal. They can be normal, but not necessary. So let's say expectation is 5 and the variance is 10 or so, then you can basically write it like this. So you're going to write it like this. You declare them here, just as the case for the normal distribution. First comes the expectation, and then comes the variance. Again, usually mu and sigma squared are associated with the normal distribution. However, this is not necessarily the case, guys. I want to stress this. Okay, so keep that in mind when you're looking at it. Okay? But if they're i.i.d, they have the same mean and they also have the same variances. Okay? That's a fact, so otherwise they would not be having the same distribution. Now, let me link that to uncorrelatedness, which is, again, uncorrelatedness or correlatedness is a much more practical concept than independency. The problem is that, I mean, okay, on the one hand, if random variables are independent, if I'm going to talk about two of them, they're also going to be uncorrelated. That's true, okay? I mean, correlation can only be addressed when it comes to two random variables, okay? Not 3, not 4, 2. Okay, so we're looking at pairwise correlation, all right? So if they're independent, they're uncorrelated. Independency technically means that there is absolutely no relationship between them at all. The definition says that their joint cumulative distribution function is equal to the product of their marginal cumulative distribution functions. That's true, okay? But this is actually what it meant to be, okay? Now, converse is not true in general, guys. So just because they're uncorrelated, I mentioned that before. Uncorrelatedness means just that there is no linear relationship between them, defined by the covariance. Okay, if they're independent, then their covariances are going to be 0. But just because their covariances are 0, it does not necessarily mean they are going to be independent. So keep that in mind when you basically consider the case of independency. So uncorrelatedness and independency are not equivalent, guys. Okay? All right? Independency is a stronger concept than uncorrelatedness. Okay? Of course, if they're correlated, then they are dependent. That's true. If there's a linear relationship between them, then there is a relationship between them. So that's going to be true. However, in case of a normal distribution, and that's also the issue why the normal distribution is so popular, the two are going to be equivalent. So if two normal variables, if I say normal, I mean following the normal distribution. If two normal variables are uncorrelated, then they're also going to be independent. It's relatively easy to show, by the way. Okay? So if they're independent, then they're also uncorrelated. That is always true. But however, if they're uncorrelated, then they are also going to be independent. So in case of normal distribution, and that's why it's so common, that's one of the reasons, of course. I mean, not the only property that it has why it's make it so attractive. Sometimes noises are assumed to be normal. You know that basically when you're looking at regression models. And one of the reasons is because, again, in case of normal random variables, independency is going to be equivalent to uncorrelatedness. Okay, that's an exception, by the way. So keep that in mind. This is just an exception. All right, that's not true in general. Okay, so please consider that. But for the normal distribution, it is true. Okay, and that is important issue. That's a fact. Okay, guys. Yes, all right. Now, let me just basically take the last, I think this is the last one from undergraduate courses. I mean, you've probably seen this before. Let's say you have two random variables and you want to consider the expectation of their sums, or expectation of sums in general, okay? So in particular, I'm talking about the sum of x and y. And that's easy, guys. The expectation of a sum is going to be always, and that is always true, the sum of the expectations, okay? So that's true, okay? Whether they're independent or not, it doesn't really matter. It can be shown, again, for that, you need to join distribution. I mean, you need the distribution of the sum, which is not very easy. You need the concept of convolution to get there, okay, which can be quite harsh. So we don't do that, okay? We're not going to calculate convolutions of random variables, but this is basically how you would confirm that. So it's, again, much more difficult to prove than you would think, okay, this case. But again, we will not need to talk about that. And then we look at the variance of their sum. Now, the variance is not going to be, in contrast to the expectation, is not going to be equal to the sum of the variances. It's going to be, I mean, it includes the sum of their variances, but then comes 2 times their covariance. And that's the point, okay? So you need to have that as well. Although variances are expectations themselves, but there is a square involved, so that's basically how you would consider it. Okay, now for the covariance, again, you need to have the joint distribution to establish that. Okay, so there is no way to address this unless you have the joint distribution in general. Anyways, now, how would you basically memorize that formula? Because I want to try to generalize this. The one way to do it is basically establishing the so-called variance covariance matrix of the two. Okay, so when you look at basically the variance covariance matrix, okay, the first is going to be actually the row index and the second is going to be the column index. You can call it like that. Okay, the covariance of a random variable with itself is going to be equal to its variance. So this means that on the main diagonal, you're going to have the variances, and every other entry is going to be considering the covariances themselves. Okay, so again, let me remind you, the covariance of a random variable with itself is going to be equal to its variance. I think this is clear. Okay, that is also true here. So on the main diagonal of the variance covariance matrix, you end up having the variances of each. And then, of course, you have the covariances here. Okay, so 2 times the covariance because you have it there twice. So what you need to see here is that the variance of a sum is not equal to the sum of the variances in general. The variance of a sum is going to be equal to the sum of the entries from the variance covariance matrix of the corresponding random variables. If you remember that, okay, then this is going to imply, of course, that in case of 2, you have the variance of the first plus the variance of the second plus 2 times the covariance of basically of the 2 because you have them here on the other diagonal in this case. You understand the point? So the variance of a sum is going to be equal to the sum of the entries from the variance covariance matrix. This is how you can generalize it. Okay? Now, most of the time it's 2, so the variance of 2 is going to be the sum of their variances plus 2 times the covariance. Now, if you have more, the expectation of their sum doesn't change. It's still going to be the sum of the expectations. So you simply bypass the sum operator by the expectation operator, by the way. I'm going to apply that quite frequently, so you'll see that quite often when addressing expectations and variances of stochastic processes and so forth. All right, so, and maybe sums and whatnot, because you have the increments that you sum up and this and that. Anyway, and the variance of the sum, again, which is not the sum of the variances, but it would be actually the sum of the entries from the variance covariance matrix. Now, the variance covariance matrix, when you got n of them, it has, of course, n entries. So it's going to be basically an n by n matrix, of course, right? And since the covariance of a random variable with itself is going to be equal to its variance, on the main diagonal, so basically here, on the main diagonal of the variance covariance matrix, you end up having the variances of each respectively. You understand the point? But it doesn't change anything if you keep that as is. So the covariance of x1 with itself is still going to be the covariance of x1 with itself. It's still going to be the variance. It's not big of a deal. Now, when you add up basically entries of matrices, I usually recommend it to use basically double sums here. Okay, so don't worry about people freak out when you see that. Okay, so if you have anything of this sort, then this just means that you need to sum up entries from a matrix. So try to basically imagine those things in terms of a matrix, and all you would find is basically that, you just need to sum up their entries, and that's it. Okay, so there is also different ways to express it, but I'm not going to. Okay, so and then if the two, namely the two's summation indices are equal, then you end up having the variances at a point. Okay, but that's just pretty much it. Okay, I think you've seen this before when you look at, you know, portfolio risk management and all that stuff, you know, return or variance of a risk of basically of your portfolio. Anyway, okay, so that's basically what I would consider. If the random variables, however, are pairwisely uncorrelated, which is the case, by the way, if they are also independent. So if they're independent, then they are also uncorrelated. That's not going to change it. Then, of course, then the covariances are going to be 0. Because if they're uncorrelated, that's basically by definition, right? But only in the case where the summation indices in the previous ones are different. Because if they are equal, then the covariance of, let's say, the first with itself is going to be the variance of the first random variable, of course. That's not 0 in general, I think. Okay, because it was then, it would degenerate to a constant. You understand what I'm saying? So that's only true regarding the covariances if the indices are different. Now, in this case, you end up having a diagonal matrix. So that's not on the slide, but if this is true, then this is going to be a diagonal matrix, having the variances on its main diagonal, right? So the variance of the first, the variance of the second, and so forth, and the variance of the last one. This is basically on the diagonal. Then that's going to become a diagonal matrix because the covariances, actually, the others are 0. Is this understandable now? Okay, I think that should be the case. Now, in this case, since those covariances are 0, you end up having the sum of the variances in case they are uncorrelated. You understand the point? Okay, so in case they are uncorrelated, the variance of their sum is going to be the sum of their variances. That's true, but only in that case, okay, because the covariances are 0 then. Okay, you understand that, guys? Okay, so don't use that as a general issue. Okay, now I'm going to slow down a little bit because this is going to probably address something which you haven't heard of. I'm not sure. I mean, you probably have, but it was not considered maybe. So again, those things until here, I assume you have seen, basically. I mean, not every detail or so, but basically what it would be. Now, in this part, I'm going to talk about convergence of random variables. And there's different types, so maybe if you want to take notes, you should, because I will need to distinguish between the two. So I have 4, 5, 6 different types, so it's going to be hard to distinguish between them. So I'm going to start off by basically convergence in distribution. That's actually the weakest form of convergence. This is actually implied by every other type. Okay, so later we're going to define also different types of convergences related to random variables, and that's the weakest one. Now, if you have a sequence of random variables, okay, which is not necessarily finite, by the way, okay, sequence is not necessarily finite, of course, but, and that is also true when it comes to random variables. So let's say you got a sequence, and each has a cumulative distribution function. Capital F1 relates to basically to the cumulative distribution function of the first. Capital F2 relates to the cumulative distribution function of the second, and so on. So each has a cumulative distribution function. And they're all different in general because the sequence of the random variables can be different, sorry. Then the sequence is set to converge to, or in distribution first, to another random variable. Okay, and that has also a distribution function, and that is going to be the distribution f function of that. So this is going to be the CDF of x, and those are the CDFs of those. All right, and that's going to be the limit. And the sequence is set to converge to the limit with cumulative distribution function, also denoted by capital F, if the cumulative distribution function converge. We talked about basically convergence of functions last time. However, this is a little bit different, okay, because in that case, or a previous case when they look at continuity, the arguments were actually converging, but here the arguments stay the same, right? They stay the same, and that's basically what you have, or if you have that, as the sequence of random variables progresses, then you'll have convergence in distributions. If you're not sure what this means, I'm going to look at specific examples, but one example will be the central limit theorem, which I'm going to address also. Okay, so the central limit theorem addresses convergence of random variables to the standard normal distribution in particular. So that will be basically converging to the distribution. Okay, sometimes you will say we're not converging to a random variable, we're converging to a distribution. But I'm going to come back to that later on. Anyway, this is denoted, okay, one thing I need to address is that in general, at those points, okay, you only have convergence at that points at which basically the commutative distribution function is continuous. And you know what a continuous function is. So I suggest basically look it up from 2 weeks ago. All right? Okay, so the image of the limits, or the limit of the image is actually equal to the image of the limit, by the way. But that's to put it in simpler terms. Anyways, okay, now if it's not continuous, then at that point you don't have convergence. So you cannot have that. That's a necessity, guys. Continuity is a necessity, but not a sufficiency for that. Okay, now why is that an issue? One of the things is basically that sometimes it happens that random variables converge in distribution to a constant. Okay, that would need to be considered in that case. But I'm not going to talk about that because you will not need this. I'm going to express this a little bit more practically in this case. So as the sequence progresses, okay, the sequence converges to its limit in distribution. So you put an arrow here, and on top you write D, which means convergence in distribution. Sometimes I also see it below the arrow, but I'm going to write it actually above it. Okay? So I prefer usually this notation. Okay? It's easy to deal with, but sometimes I use basically the other. Okay, because again, that's not a practical concept in that case, but it will play a huge role. Now, there is also a different way to express it without the commutative distribution functions, because the commutative distribution functions, as you see, okay, so keep that in mind. Don't let this confuse you. This thing is the commutative distribution function of each respective one at point small x. Okay, that's it. And the limit of that, as you saw, supposed to be the commutative distribution function, which is the commutative distribution function of the random variable to the limit at point small x as well, at which basically the limiting commutative distribution function is continuous. Now, if you want to have a definition without them, okay, you need to understand that this is equal to the probability, or that if, the limit of that is equal to the probability that x, which is the limiting random variable here, does not take values that are greater than small x, which is, on the other hand, being equal to the cumulative distribution function of the limiting random variable. Okay, so sometimes I use even that one. Okay, so that is a very, actually, weak convergence, by the way. Okay, so that's a weak one. That's actually the weakest one there is when it comes to random variables, because every other type of convergence is implying convergence in distribution. But I'm going to come back to that later on. Okay? Again, you'll see an example, but one of the most famous examples is going to be the central limit theorem. I'm going to put that also formally, so you see that later on. The second type, if you want to take notes, is convergence in probability. Convergence in probability is said to be the case if and this is something which is important, okay, so the sequence is set to, a sequence of random variables, of course, is set to converge in probability to another, let's say, to the limit, that's the limit. Okay, so that would supposed to be the limiting random variable. If the probability that this does not happen, okay, is converging to 0. So the probability that the two basically do not converge, or the sequence does not converge to x, is going to be 0. And when does it happen? It happens if the distance between the members to the limit is exceeding a certain value. Because if this is happening, okay, then it would indicate that this is not, it's not converging. Okay, so epsilon is just a distance. Okay, it's a prefix distance no matter what. And the probability that basically the member or the distance of the member to the limit is exceeding that is supposed to converge to 0. Okay, which means that it's less and less likely to be basically the case that a member is having a distance which is greater than a specified value, which I call it epsilon. Okay, so let's say epsilon is, you set epsilon to be equal to 0.1, and that must be true for all, not just for 0.1, but you make it understand it better. Okay, as the sequence progresses, it's going to be less likely that the members exceed that distance to the limit by, which is exceeding by 0.1. Okay? So the probability that basically the members exceeding, or the distance of the members in the limit is going to exceed 0.1 is converged to 0. So it's going to be less and less likely as the sequence progresses. If you're not sure what this means, I'm going to basically elaborate on that a little bit longer. Okay? So this is denoted by the following notation. So you have a P here. Okay, so you have an arrow with D, which means convergence distribution, and now you have an arrow with P, which means convergence and probability. It's a stronger concept, okay, because convergence and probability implies convergence distribution. So the probability that, so to put it in simple terms, the probability that the distance between, okay, so this is the distance, right? I should have basically considered the distance function, actually, as I recall it, but okay, we're going to take the absolute value. I'm going to use the univariate case, so we're going to stay to that. That's the only distance function there is. When a one-dimensional case, we're not going to look at vectors, so why would we? Anyways, so so inside the difference of the absolute, this is the distance of the member to the limit. And the probability that the distance of the member to the limit exceeding a certain value is going to converge to 0, which means that it's going to be less and less likely as the sequence progresses. The weak law of large numbers is going to be a famous example on that, so I'm going to talk about that later on, where the sample mean is converging to the population mean in probability. I'm going to address that later on. Okay, so that's one famous issue. Anyways, I'm going to look at the next one, almost short convergence. I'm not going to apply this frequently, but I'm talking about that sometimes here and there. Okay, so we say that the sequence converges almost surely. Remember that term, almost surely? An event is set to happen almost surely if the probability that it is happening is equal to 1. So this is basically mean that they're converging, right? So the probability they do is going to be equal to 1. That's the strongest so far. Okay, so this implies actually every other. So if random variables converge almost surely, they're also converge in probability and they're also converge in distribution. But I'm going to summarize it later on. Okay, now in this case, you write it like this. AS means you have A point, S point, right? So this means that almost surely, okay, you have almost sure convergence. Again, I prefer this notation, okay, but you can also use that one. Keep in mind, when you have convergence in probability, this means that the probability that the sequence converges is equal to 1. Okay, almost surely, right? So they converge almost surely. This is literally that. Okay, I'm not sure if you remember that term. Maybe you could watch the video from 2 weeks ago. All right. Okay, and the last thing that I'm going to look at is convergence in mean. If you have convergence in mean, in particular convergence in rth mean, and R is a value which is, let's say, at least 1. It could be 2, 3, 4, 5, but not just integers. It can also be something else, but in practice, you only consider the first, the second, the third moment, and so on. If, again, so given R, which is given, at least 1, so 1 or more, if the limit of the expectation as the sequence progresses, or let's say the distance, okay, to the power of r. Okay, so inside the absolute value, you see the distance of the member to its limit to the power of r, as you see, right, is going to be the rth distance, you can say. And then the expectation of that, if the expectation converges to 0, okay, then this is actually meaning that you have convergence in mean. Okay, that's another type of convergence. The most common one is convergence in mean square, or mean square convergence. I'm going to talk about that as well. Okay, but that's going to be also an issue. Yes, all right. I'm not sure if you remember that. Okay, so the expectations converge somehow, and other moments too. All right, but I'm going to look at. Now the notation is looking like this. R, so you have L, and a little r, basically written down like this. This is honoring Lebesgue, so L stands for a French mathematician. He's called Lebesgue, okay, because there is the Lebesgue, so-called Lebesgue measure involved, but that's something you don't need to know, okay? And that's a notation which is written on the arrow, okay? Okay, so again, you'll see. I'm going to summarize those, and then there's going to be a specific case, convergence in mean square. Okay, so they are set to converge in mean square, which is referred to as the mean square convergence. This is basically what you're going to see. Okay, I'm going to finish that one. Square means this parameter that you just saw is 2 then. Okay, so R is 2. That's a specific one. And that's the most common one. So when we're basically looking at it. Okay, why? I'm going to address this later on. So when it comes to stochastic processes, especially basically that, then we're going to end up looking at this as well. Okay, so in this case, you could change it to L to the power of 2, right? So L squared, again, L stands for Lebesgue because the so-called Lebesgue measure is involved, but again, I'm not going to talk about that here. Or you could simply write down MS. So MS mean squares, right? Or sometimes I see that too. I think Mr. Hustle does that, just that. Okay? I think in his book, if I recall it correctly, I'm not sure, he uses that. So just simply write down 2. Convergence in mean square. Okay? So the expectation of the square of the distance between the member to its limit is converging to 0. The expectation of the square is converging to 0, right? Does that make sense? Okay, I hope it does. Anyway, I'm going to summarize this. So if you kind of lose track, which is understandable, I'm going to summarize basically what these things were. Okay, so here you saw basically convergence in rth mean, which means that the distance of the member to the limit, to the power of r, or the expected distance, or the expected rth power of the distance of the member to its limit is going to converge to 0. That's convergence in mean, or in particular, convergence in rth mean. There is, again, so this is the list. There is almost sure convergence. What does that mean? This means that the probability that the sequence converges to a limit is going to be equal to 1. Okay, so dark blue X is always the limit, by the way, right? That's something which you should keep in mind by now. Okay, now what does the probability means? Okay, so convergence in probability means what? The convergence in probability does not mean that the probability is going to be equal to 0, that they don't converge. This means that the probability that they don't converge is going to converge to 0. So that's a weaker concept, right? Okay, so to put it in simpler terms, okay? Because if, let's say, to put it in simpler terms, the distance, okay, so this is always a distance. So when it comes to the absolute value of a difference, this is always going to be a distance between the two. So the distance of the member to the limit exceeding a certain value, or the probability of that, is going to converge to 0. So if the distance of the member to the limit exceed a certain value, that this might indicate that they don't converge. So that can happen, but it's going to be less likely as the sequence progresses. You understand what I'm saying? So it's going to be less and less and less likely that they don't converge as the sequence progresses. And here, it's always going to be 1 from the beginning. That's the difference between the two. You understand? So you don't have actually the probability that converges. Okay, where here it does. Now, of course, in contrast, so let me basically stress that one, because this is going to be it. So, I mean, this is going to be equal to, I mean, this on the other hand, the probability that they do. Okay, so let me basically address that one, which means that they are less than or equal to epsilon. So the probability that they do, on the other hand, this is basically what you need to understand here. So the probability that they do, the members, okay, so they do converge, is going to be equal to 1 then. The probability is going to converge to 1, sorry. You understand the point now? Okay, again, and the last thing was convergence in distribution, which means that the cumulative distribution function converge. They do, okay, which you see here. So keep in mind, okay, on the left, this is, oh, sorry, on the right, which is the limit, this is the cumulative distribution function of the random variable capital X at point small x. So small x is here. All right, that should be denoted. And those that are also involved, which I'm going to consider here, those are the probability mass functions of the respective random variables, each at point x. Of course, I need to say that at points at which the limiting cumulative distribution function is continuous. All right, so that's basically pretty much it. Okay, now, okay, I suggest taking a break now, and then we're going to continue basically considering those types of convergences. Okay? Okay, so we're going to take a break of 15 to 20 minutes. Be back at 6 o'clock, okay, and then we'll finish it. All right? Okay. I'm going to stop here a little bit. All right, guys, I was not sure where that was. Sorry. Okay. Convergence and probability. We had those parts. I apologize. I thought, yeah, we come relatively far. It was here. Yes, that was it. I remember. Okay. Taking that one. Okay, well, convergence and distribution, that was the last part. I apologize. Okay, so we have also different notations here for that. Same thing, so here again, LR, convergence in arith mean, AS for almost sure convergence, P for convergence and probability, and D for convergence and distribution. All right, guys. Now, there is another statement which I want to do, and later we're going to prove at least one of the, or I mean some of the, basically of these implications. For example, the first implication is that almost sure convergence implies, as I mentioned before, convergence and probability. So that's the first implication, okay? Then convergence and probability implies, on the other hand, convergence and distribution. I mentioned that before, so that should be clear, right? Now, regarding the convergence in arith mean, there is no direct relationship between convergence in arith mean and almost sure convergence, but there is actually a relationship between convergence in arith mean and to a smaller mean. So convergence in arith mean, or convergence in mean, implies convergence in the smaller mean. So S arith mean and S mean is basically the issue. R is greater than S. So let's say convergence in mean squared convergence, basically. Convergence implies convergence in mean. So R is greater than S, and if R is greater than S, then it's going to be applied here, and of course both are not less than 1. Okay, so both are at least 1, and R is strictly greater than S. If this is the case, then of course convergence in R mean implies convergence in smaller mean. That's what it is. And however, convergence in the smaller mean, or convergence in mean in general, implies convergence in probability. So that is true. Okay, so this is basically how it looks. If you're not sure and not understanding it, okay, so again, convergence in mean implies convergence in smaller mean. Let me write it like this, rather like that. So let's say basically this is it. Okay, now I'm going to start with basically almost short convergence. Almost short convergence implies convergence in probability. Convergence in probability implies convergence in distribution. Okay, I think that is clear. And convergence in mean implies convergence in smaller mean. Okay, because again, I stress R is greater than S, or S is less than R. And convergence in mean, however, if both are at least 1, it doesn't really matter, implies convergence in probability. So that's a chain. However, there is no direct link between those two. Okay, so although actually almost short convergence is one of the strongest ones, there is no direct indication between that and convergence in mean. Okay, so that's basically the chain of the implications. Is it clear? Okay, now I'm going to prove one of the two. So I'm going to prove that one, and I'm going to prove that one, and I'm going to prove that one. So those three, we're going to see why. Okay, so how come this and that? It's not difficult actually to prove those. Okay, but I'm going to discuss basically further properties. So for example, again, I will need to basically mention two important issues, which is the central limit theorem and the weak law of large numbers. So let's say you got a sequence of random variables, and in this time, there are i.i.d. even. Okay, so they're independent and identically distributed. Okay, so independent and identically distributed, which means that if they're independent, they're mutually independent. Okay, and this also implies that you're uncorrelated, of course, so their covariances are going to be 0, and they have the same distribution. So identically distributed means just that they have the same distribution respectively. Okay, so if the first is standard normal, then every other is going to be standard normal. Okay, in this case, so they are i.i.d. Thus, they have identical cumulative distribution functions with identical means, identical variances, and so on. We talked about that in detail. Okay. Now, this is not the sequence that will converge, okay, because that's not the sequence that I will, because they have the same distributions, okay? So if they have the same distributions, I mean, they do converge, but they are the same. Now, let's say their expectations are mu, respectively, and their variances are equal to sigma squared. Again, please do not associate this issue with the normal distribution. Okay, I know that a lot of times when it comes to the normal distribution, this parameter is called mu and that parameter is going to be sigma, but that's not the point. Okay, so based on those i.i.d. variables, I'm going to define their corresponding sample mean or the arithmetic mean. You know what the arithmetic mean is? The arithmetic mean is the sum of those random variables divided by their number of random variables. So that's going to be the arithmetic mean. And that actually indicates a sequence of arithmetic means. Okay? So now, before we address that issue, I'm going to address the expectation and the variance of the arithmetic mean based on the properties that we just saw previously regarding the expectation and variances of linear transformations and sums. Keep in mind that the arithmetic mean is also a linear transformation of a random variable, because if those are random variables, then the sum of them is also 1. So if the sum is a random variable and you multiply a sum by a constant, you're going to get a linear transformation of that random variable. Now, if you want to consider the expectation of that, you need to remember that the expectation of a linear transformation is the linear transformation of the expectation. And the expectation of the sum, on the other hand, is going to be the sum of the expectations. So you simply take out the multiplicative constant from the expectation operator as you see it, and you simply bypass the expectation operator by the sum. So the expectation of a sum is the sum of the expectations. You simply, okay, so you break into it. That's basically it. And what are the expectations? The expectations are here. They are mu respectively. So the expectation of the arithmetic mean as this follows, okay? Again, the expectations are mu, which they are these constants, so you see them, okay? There are these sums of these mu's, okay? So you got mu plus mu plus mu plus mu in total n times. So 1 by n times actually the sum of these mu's is equal to 1 by n times these mu's, and that equals actually mu. So when it comes to this, the expectation of the arithmetic mean is equal to the expectation of the respective random variables from which the arithmetic mean was constructed from. You understand the point? Okay, so that's one of the issues that I would need to address. Okay, so that the expectation of the arithmetic mean is just as large as the expectation of their respective random variables from which your arithmetic mean was generated from. Now, I'm going to look at the variance. Okay, so that's one major result. I'm going to come back to it, and I'm going to look at the variance of the arithmetic mean. The variance of the arithmetic mean, however, is going to be different. Keep in mind that the variance of a linear transformation, that is a linear transformation of the sum, and the sum is the random variable. So you see basically it. The variance of a linear transformation is not the linear transformation of the variance. When it comes to basically linear transformations, the variance of a linear transformation is going to be the square of the multiplicative constant times the variance. So you want to take out 1 by n from the variance operator. You can, it's multiplicative, so you can, but you need to square it. This is going to be 1 by n squared then, because 1 by n squared is the square of 1 by n. You understand the point? So that's going to yield the square of the multiplicative constant, which you see now, times the variance of the sum. And that's basically what you end up with, at least at this stage. You understand it now? Now, the variance of a sum is not the sum of the variance, as I mentioned before. The variance of a sum is equal to the sum of the entries from the variance covariance matrix, as you saw in the first part. However, the random variables are independent. And this means also that they are uncorrelated. If they are uncorrelated, which means that the covariances are 0 respectively, then the variance of a sum is going to become the sum of their variances. So you basically end up with 1 by n squared times the variance of their sums. You understand? And this is due to the fact, so this equality here is due to the fact that they are independent, which means that they are also uncorrelated. Okay, if they're independent or if they're uncorrelated, then the variance of their sum is going to be the sum of their variances. You understand? And that's basically what I'm using here. So you can simply bypass the variance operator by the sum, which basically we did, okay, if they're independent. That's why I was assuming that to be the case. If they're not, then I got an issue, okay? So then you would need to consider the covariances also, but that's something that I can't do. Now, what are the variances? You see them. The variances are those constants, namely sigma squared. So you end up basically summing up those sigma squared, and you have 1 by n squared times the sum of those sigma squared equals actually 1 by n squared times n times those sigma squares. Okay, because you sum them up n times. So you have n times sigma squared. And 1 by n squared times n times sigma squared is going to be, however, sigma squared by n. So what you see is that actually the variance, in contrast to the expectation, the variance of the sample mean is not going to be actually equal to the variance of their respective random variables from which the sample mean was generated, in contrast to the expectation. And this is basically indicating that this is going to decrease by the sample size. So the variance decreases by the variance of the sample mean decreases by the sample size. It's a very important result, by the way. And to get there, I was using the expectation and variance of linear transformations and sums. That's the most common thing. And those are the things that you will need to apply when it comes to stochastic processes too. So we're going to practice it this time. I'm going to take that and put it in an exercise. Okay, so you would need to basically get there. All right? Okay. Now the variance of the sample mean, okay, and the expectation of the sample mean can be used to standardize the sample mean, which is going to be required when it comes to the standard normal distribution. I want to have the convergence related to the standard normal distribution. How would you standardize it? It's simple. You're simply taking it as it is, subtract its mean. Its mean is going to be equal to the mean of the respective random variables. By the way, that's true. And dividing it by the standard deviation. Now, however, the standard deviation is not going to be sigma, although the standard deviation of the respective random variables is sigma. You need to standardize the sample mean and not the random variables. If you standardize the random variables, let's say xi, you subtract its mean and dividing it by its standard deviation. However, the standard deviation of the sample mean is not going to be sigma. It is sigma by the square root of n, because the standard deviation of the sample mean is going to be the standard deviation of that, and the standard deviation of basically of sigma, the square root basically of sigma squared by n is going to be sigma by the square root of n. So I'm going to divide by sigma by the square root of n this expression, and that's going to be its standardization. Now, when it comes to standardization, guys, and you can check it very quickly, I want you to basically to remember that I'm calling the standardization Z to make it easier, and you could check basically for the expectation and for the variance. Okay, so I want you to basically to address those. The expectation of the standardization is, as you might remember, is always going to be 0 no matter what you're standardizing. It's always going to be 0. And the variance of the standardization, however, is always going to be equal to 1. And that is also true for this one. Okay, I'm going to create an exercise later on. So somebody asked me, basically for exercises, I'm going to provide you them, but I'll need to conceptualize those. Okay, I apologize. It takes a little more time. I want to get the readers first and then the exercises. Okay, so that's basically how you end up with, and that is, again, what this is going to be in this case, though, however. Okay, now, you can also write it differently, which is actually done in practice, because if you divide it by the square root of n inside the denominator, so the denominator is here, this is actually by multiplying it by its reciprocal, and the reciprocal of basically of 1 by the square root of n is going to be n, and that's basically what I'm doing here. Okay, so I'm multiplying it by its reciprocal. That's going to be the same expression. Okay, so that is also the standardization that has the mean 0 and the variance 1. Okay, now that makes basically creating the central limit theorem much easier, and that was the reason why I did it. Okay, because as you see, this is the sample mean up there, and down there, this is its standardization. Okay, so what you see is the standardization of the sample mean, but I needed to get there, and I needed to have the expectation and the variance of the sample mean. Okay, now when it comes to the central limit theorem, which I'm going to basically establish right there, the central limit theorem claims that the standardized version, first off, I would need to consider a sequence, because the arithmetic mean defines a sequence of itself. If you're not sure why, okay, I'm going to give you an example. So let's say you got the random variables first, which are here. Let's say the first observation or so is 2. The second observation is 5. The third observation, let's say, okay, I'm not going to continue for that, but that's something, let's say is 2 again. And I'm going to create the arithmetic mean, basically of the first observation is the sum of the first observation by the number of observations. You just got one of them. So that's going to be 2, of course, right? The arithmetic mean based on the first 2 observations is going to be 2 plus 5 is 7 by 2 is going to be 3.5. You understand that, guys? Okay, and the arithmetic mean of the first 3 observations is going to be 2 plus 5 plus 2 is 9 by 3 is going to be actually 3. Okay, so this is the sequence of arithmetic means. Okay, I'm talking about that. You understand the point? And that is implicitly defined here. So if it says x bar n, that means the sequence of arithmetic means of the first, consisting of the first n observations from this sequence. So that is a series, guys. If you sum up members of a sequence, you're going to get a series. So the arithmetic mean is actually a series, guys. You see that? Defining a series with basically the index n. Is that clear, guys? Okay, I'm not going to continue, but that should be actually understandable. All right, now this defines a sequence itself, and that sequence converges in distribution. And the central limit theorem claims that if the summands are i.i.d, then the series, or the standardized series, again, here it is, in this case, which is the arithmetic mean, will converge in distribution to the standard normal distribution. Okay, so again, first off, you have the series of arithmetic means, and then you have basically that their standardization will converge to the standard normal distribution. Now, this notation might be disturbing because that is not a random variable, but you can also say like, okay, this converges to, let's say, z, where z is following the standard normal distribution, okay? So then, of course, you could simply replace the random variable by the name of the distribution to which it converges to. That's it, okay? It's not a big issue, okay? So whether I will declare z to be, let's say, standard normal, or basically the limit to be the standard normal distribution, is actually irrelevant. You understand the point? I will not need to define a random variable here. Does that make sense? Okay, so that is basically it. And that's the claim. And this is a very famous and very important one, and one of the most important one there is. Okay, so I would like you to basically consider it. So this means that if those are i.i.d, which means they have the same distribution, they're independent, right? Then the sequence, the corresponding sequence of their sample means converges in distribution to the standard normal distribution according to the central limit theorem. Now, I'm not going to prove it. I'm going to give you the proof, okay? So it's astonishingly easy when you know something about characteristic functions, but I mean, I have half an hour left, so I will not going to basically go into that. So that's something I'm not going to prove here, okay, basically, but that's something you should be understanding here. Now, you can also write it differently, which, again, is a different notation. So the limit of the probability that basically, and what you see here is the cumulative distribution function of the standardized arithmetic mean is going to converge as the sequence progresses to phi at that point, at the same point, you see? So phi is the cumulative distribution function of the standard normal distribution. And that is basically the same thing. So this is just expressing the central limit theorem in terms of a different notation. Okay, but most of the time I prefer the other. Okay, you need to understand that this is the standardized version of the sample mean. All right, so that's a very famous theorem, which I'm not going to prove, but when you look into the readers, you're going to see how this works, so you can check it out there. Okay, and of course at point x, at every point there is, okay, because this is a continuous function. So, well, that's the issue, okay? Now, keep in mind, guys, okay, so here you see the definition. I mean, that's not it. There is no, this is a semi-closed form solution, okay? It's not an explicit one because there is no primitive function or no explicit primitive function or a closed form function of the density or the primitive function of the density of the standard normal distribution, sorry. Okay, so again, it can be shown, but it's a semi-closed form. Okay, so in this case, this integral can be calculated, but only numerically. Anyways, okay, so that's basically how it would be, and that is on the left-hand side, the cumulative distribution function. This one, I'm talking about that one. This is the cumulative distribution function of the standardized sample mean, and that's going to converge to that of the standard normal distribution. Now, the point is, and that's a very important one, no matter what the distribution is, every distribution will converge as far as their respective sample means are concerned, or the sample mean of every distribution, let's say, that's an easy one, is going to converge to the normal distribution provided they have the same distribution respectively. It doesn't matter what kind of distribution it is, as long as it's the same, okay? And they're independent. In this case, that's going to work, okay? If they're independent, and they have the same distribution. There is multiple variation or multiple versions of the central limit theorem. That was the first one. I mean, not just the first one, the second one. The generalization, basically, for the binomial distribution. So that was proven first, and that was a generalization. So that is true across the board for every distribution there is, as long as the variables are independent and they having the same distribution. Okay, you probably heard about that. Okay, I'm not going to apply it here. I'm going to look at stochastic processes, and we're going to apply that when it comes to functional analysis. Now, again, let's go back. This is a more compact notation. You don't need to have distribution functions, none of that stuff. So I think I prefer that one. That's all you have is the standardized mean, and the standardized arithmetic mean of those random variables. And the standardized version of the arithmetic mean is converging in distribution to that of, to the standard normal distribution according to the central limit theorem. This is the Lindenberg-Levy version, by the way. Anyways, I'm going to continue, and I'm going to basically also address the weak law of large numbers first. The weak law of large numbers, okay, you have the same consideration. You have i.i.d. random variables, each having the respective mean, which is mu, and the same variance, which is sigma squared respectively for each. If this is the case, then, and that's basically what you're going to end up with, the sample mean of those random variables, not the standardized version, is going to converge to the population mean, which is actually the expectation of those random variables, namely in probability. Okay, so that's basically the weak law of large numbers. Okay, and there is also the strong version, which is actually a stronger case, okay, so convergence in probability. We're going to prove that also. So we're going to prove the weak law of large numbers. It's astonishingly easy to prove. And we're going to look at the strong version. However, it's much difficult to prove, and so it's not very common. And it's also a stronger condition. So again, almost sure convergence is also a stronger condition or a stronger convergence type than, let's say, convergence in probability, because convergence in probability is implied by almost sure convergence. So it is a strong and a weak version, sorry, of the weak law, of the law of large numbers, LLN, which I call them, okay, and CLT was a central limit theorem. I'm not going to prove that one, but that is also true, however. And yeah, so again, let's go back to the weak version. How to prove it? That's not big of a deal. Let's recall that the expectation of the sample mean was mu, and the variance of the sample mean was sigma squared by n. This is something which we have already addressed, so we don't need to address it again, okay, but you need to prepare that, okay, so that's how you would establish it. And Chebyshev inequality is the tool that we're using. Now, of course, we're not going to prove that one. This is a more fundamental result, okay, than that, but this is just an application of that. So the Chebyshev inequality is going to claim the following. If a random variable, which I call x here this time, is having the expectation a, and its variance is, let's say, equal to b, then the probability that the random variable does not exceed its expectation, which it is here, okay, so not exceeding its expectation by a certain value, okay, is not going to be greater than basically the variance by the square of that certain value that is not exceeding, okay, so that's the claim, okay, so this is give you an upper end point of a probability that a random variable is further away from its mean than, let's say, epsilon, which is a predefined distance. You understand the point? I'm not sure if this is clear, okay? Now, if the distance is very small, okay, now this is going to be relatively large, so it doesn't make that much sense if, let's say, the square of that is not greater than the variance of the random variable. But it doesn't really matter, okay? So, if it's equal, then it's going to be equal to 1. But anyway, this is going to be what I use here on the sample mean. So I'm going to substitute basically x by the sample mean. And I'm going to substitute a by mu, and I'm going to substitute b by sigma squared by n, and apply the Chebyshev inequality on that. So when you basically put those things together, which I do, okay, the probability that the sample mean, okay, is not further away from its expectation than, let's say, a predefined distance, which is epsilon, the probability of that actually the distance of the sample mean and the population mean, which is mu, exceeding a certain value is not going to be greater than the variance of the sample mean, which is sigma squared by n, divided by the square of the distance that is not supposed to basically exceeding. Okay, so that's just simply putting together the Chebyshev's inequality and applying it on the sample mean of those random variables. And you need to have the mean and the variance for that. Okay, now this is going to be interesting because if this is true, okay, which it is, you got a question?
Why do we square epsilon here?
This is something that you should basically look into the claim of that. Okay, I mean, I could also address that one, but this is more sophisticated to prove.
Like in simple terms, is it just to make the whole concept stronger?
I'm not sure what you mean by that, but actually I'm basically just applying this inequality. So of course I'm not proving it. Okay. That's more sophisticated to do. But I'm taking that as a result and build that into considering that for the weak law of large numbers. Okay, so that's basically what I did. Okay, there is a substitute. Yeah, you got a question? Maybe I'm not sure if I understand what you have said. No worries.
Does the concept of convergence of the sample mean to the population mean
yes.
Anything to do with the concept of ergodicity?
Ergodicity, yes. But that's relating to stochastic processes. Okay, that's true. Okay. All right, so satisfying basically a sample mean of a stochastic process satisfies basically the weak law of large numbers. That's it. But I'm not supposed to. Maybe we'll look at that one as well. Okay, but ergodicity is a concept which is important. Yes, but I don't have stochastic processes here. So now, but you can consider them to be random variables. Now, the limit of the left-hand side on that one is of course the limit on the right-hand side. Okay, so that's a consequence. Okay, so again, if A is not greater than B, then the limit of A is not going to be greater than the limit of B, right? So that's also actually, it is. If the members are never going to be less, then their limit is not going to be less either, all right? If there is one, which there is, because this has a limit. I'm not sure if you see that one, but the limit of that is going to be 0. So basically by addressing this, as a sequence progresses, this means that the probability that the members from this series, which is the arithmetic mean, okay, having distances to their population means, which is always going to be mu, by the way, which is exceeding a certain value, is going to converge to 0. And that's basically, by definition, convergence in probability. All right, so that's the same issue. So here you see the same thing again. Okay, I will take it off. So I would just basically put it together. And that's, by definition, convergence in probability. So this converges in probability to that constant, by the way, by definition. And that's the proof. Okay, astonishingly easy if you just basically consider the Chebyshev inequality, which we did. All right. It's not a big deal, right? Of course. Now, I'm going to prove the others. So I'm going to show you that I mentioned before. First off, I'm going to show you that convergence in mean implies convergence in lower mean. I was addressing that one. Here it is. Okay, so if R is if R is greater than S, here it is, then S is the lower mean, all right? And that's going to be the first one. Okay, both are actually at least 1. That should be noted. Then I'm going to show you that basically based on that, convergence in mean implies, you don't need to name that. I haven't done it here, but it doesn't really matter. Convergence in mean implies convergence in probability. Okay, so this implies, on the other hand, that. Okay, you could also replace it by S, of course, right? So it doesn't really matter because S is also at least equal to 1, but it doesn't matter, so you can take R as whatever you like. Okay, so as the sequence progresses. Okay, so that's the second part. That's not going to be difficult either. I'm not expecting you to do it, but I was just using some inequalities that I was looking up and then putting those together. So somebody else did that. I was just putting all together the pieces. And finally, I'm going to show you, that's going to be more interesting, that convergence in probability is basically implying convergence in distribution. So if random variables converge in probability, they're also converge in distribution. That's going to be the third one, which is the most interesting one, as I think, but that's also the easiest one. Okay, you're going to see when you look at some tools that stochastics are going to be provided, yeah, well, you can apply them relatively easily. Okay, so the first part was that convergence in mean is implying convergence in the lower mean. And the inequality that I looked up for that there is also a more general case, was Hurdle's inequality. Okay, you will not need that for the exam. Okay, I mean, if you do, then I would give it to you, so you will not need those. Okay, there's a Chebyshev inequality, lots of inequalities that I'm going to use. It says the following. So if you have the absolute value of the expectation of the absolute value of a product of two random variables, that's not going to be greater. So the mean of that is not going to be greater than the product of their means, whereas the first one is going to be the expectation of the absolute value to the power of p, which is a parameter, and the expectation on the other hand is going to be actually to the basically to the power of 1 by p. Keep that in mind that those two don't eliminate each other, because you cannot take p out from the expectation operator. The expectation operator is a linear operator. So if you're not sure why, just to remind you that the expectation of the square is not the square of the expectation in general. Okay, so you cannot take those exponents out from the expectation operator as you would like to, because if you could, that you could basically cancel those, but you cannot. Okay, you understand the point? So if you translate it to that, and this is basically, let's say p is equal to 2, then that would be the square root of that. Okay, is not going to be, and that's basically the point. Okay, I mean, this is the expression that you're referring to, because to the power of 1 by p, if p is equal to 2, then that's going to be the square root of that. Okay, and that is going to be not greater, so the expectation of that is not going to be greater than the product of these two means, where you have another parameter here. So these parameters are interchangeable, and keep in mind those parameters can be even infinitely large. Okay, so there is also the version where actually p, or at least one of the two, would converge to infinity, by the way, but that's something which I'm not going to address now. Okay, so I was using that just relatively simple version. There is only one restriction though. 1 by p plus 1 by q is going to be equal to 1. That should be the case, right? So if p is equal to 2, then you would take the second root, and you would need to also have q is equal to 2 as well, because otherwise it would not work. Anyways, okay, so those are the things that are to be considered. Again, p and q are parameters that you can choose. And I'm going to substitute accordingly. So just for the moment, because again, I'm going to address convergence in mean. So I'm going to first off substitute a by this expression, which is familiar, related to convergence in smaller mean. Again, you can see. And the other random variable is going to be just set to a constant. So that is also true for constants even. But constants do not have expectations. But it doesn't matter. Okay, and p is going to be r by s. And you need to understand that r is greater than s by definition. Okay, so because convergence in rth mean and convergence in lower mean, which is s, so r by s is greater than 1. Okay, so that should be denoted here. Okay, so p actually is satisfying this condition. I wanted to make that sure basically by using this substitute. Anyway, okay, so now I'm going to put it together. Now I'm going to consider the expectation of the absolute value of a times the absolute value of b. Now, since the absolute value of 1 is not an issue, I could take it out. Okay, so that's going to degenerate to this expression. The absolute value of a times b is going to degenerate to a times 1 in this regard. And that's not going to be greater than the product of the means of a. Now, this is going to be kept here, so I'm not substituting that one, not now, at least not now. Okay, here you're going to see that. And I'm going to basically, this is a, this is to the power of p, okay, so that's corresponding to that, and the whole thing, the expectation is going to take into the power 1 by p, and here you have the expectation of b, which is equal to 1. I mean, this thing will degenerate to 1 if b is a constant, and in particular is equal to 1, so that's basically to what's to what it generates to. And I'm going to look at that expression a little bit carefully because you can see that you are inside the expectation operator. Okay, so inside the expectation operator, it's not clear because there's too many brackets and so forth. Okay, so here you're inside the expectation operator. Okay, I'm going to use the black one. Okay, so here in the former, you got to the power of s. And this thing is taken to the power of r by s. And if you take the power of power, you multiply the exponents. You understand what I'm saying? So then you can cancel s and you're left with r. That's it. Okay, so this is basically, you should keep in mind. Okay, then you can eliminate those. And I'm going to rewrite them again. So this is it. Okay, I'm going to ignore this. And what you see here is the following. I'm going to introduce you to that. If this thing, okay, I mean, one of the things that I need to mention is this. This is not going to be, this expression is not going to be greater, whatever that is, than basically the expression here. Okay, so if you're not sure why, okay, so again, let's say p is equal to 2, just for the record. Then this means, okay, something, let's say 5 to the power of 1 by 2, which is the square root of 5. So that means the square root of 5 is not going to be greater than 5, which is true, right? So you can clearly see that this is it, right? So that's basically the issue because p is greater than 1. And that is also true for the expectation because the expectation is a constant, goddammit, right? So that's pretty much it. So whatever that is, it's not going to be greater than that. Now, so that's why I was not substituting here because p is greater than 1. Okay, so you would not need to substitute there. Now, why is this important? Because whatever happens to that, if this converges to 0, which means that you, as the sequence progresses, which means that you do have, and that's the point, you do have convergence in rth mean. That's it by definition. This expectation is converging to 0. Then, now, this is the upper end point, guys. So this thing will converge to 0. This is going to be the upper end point for the other. You see? That must also converge to 0 then, as the sequence progresses. Okay? Because it's not going to be greater than that, right? If something is not greater than 0, never, okay, and the limit here is that is going to be 0, that must be also converge to 0, so this thing will converge to 0 too. And that's basically proving the issue that if you have, and that's what I'm basically going to stress here, convergence in rth mean, which that it is, okay, so this is basically convergence in rth mean, okay, then you do have convergence in the lower mean, which is here. Okay, so that is convergence in lower mean, because as you see, okay, looking at this expression, R is greater than S. That's proving this issue. So convergence in mean is implying convergence in lower mean. You understand the point? Okay? Now, so, okay, I'm going to basically discuss it in detail, but that's the issue. Now, next, I'm going, and that's astonishingly similar, so the structure of the proof is going to be the same. Convergence in mean implies convergence in probability. Okay, I'm going to talk about that. So basically, for that, I'm going to use Markov's inequality referred to a certain probability. This means that the probability that the absolute value of a random variable, okay, is exceeding, let's say, a certain value, which is delta here, is not going to be greater, whatever that probability is, okay, is not going to be greater than the expectation of the absolute value of the random variable. Okay, so that's, again, if you ask me why this is, I would basically reference Googling to proving Markov's inequality, so you can check that out if you want to do it. But that's more complicated to prove, of course. Okay, so I don't going to waste your time. I mean, okay, so by this distance, okay, so this is also, let's say, addressing basically a certain issue, not for basically the maximum probability, not by the variance of a random variable, but by its expectation, in contrast to the Chebyshev's inequality, right? Now, you can substitute again, by the same thing, and I'm going to substitute the distance by e to the power of r. I'm going to show you why. Now, sorry, not e, epsilon, which is a predefined distance, whatever it is. And I'm going to plug it in. So you got the probability here that the sequence, okay, is exceeding the limit or the distance of that. I mean, this is a distance function too, to the power of r, of course. Okay, so you can see that here. being at least epsilon to the power of r. And that's why I was choosing basically delta to be epsilon to the power of r, because I can then eliminate r. R is at least 1. Okay, so that's basically the issue. So you can simply take the rth root inside basically the inequality, and that's not going to change because that is a strictly increasing function. So if this is true, then that is also going to be true if it's not there. So then you're getting rid of the exponent. And what does that remind you of? This reminds you actually on the definition of basically convergence and probability. Okay, because this is going to converge to 0 after all. Okay, so if r is not there, let me just basically eliminate it. The fact that this probability converges to 0 is actually defining convergence and probability, by the way. Okay, so the probability that the distance between the members of the sequence to the limit is exceeding a certain value is converging to 0. After all, why? Because that is still true, right? Still, we have convergence in mean. So if you have convergence in mean, you have also convergence in probability. This is the implication that is proven here. Astonishingly easy to prove. Okay, I got 10 minutes left, so that's going to be fine for the rest. Okay, that's not going to be difficult. Now, if you want to prove that convergence in probability is implying convergence in distribution, okay, you need to have another trick, and that is just, that has no name. I mean, I couldn't find it, so I don't know what to look for. So I'm going to put, if you want to prove that, at least, I'm going to put it there. So when considering two random variables, the probability of one not exceeding a certain value is not going to be greater than the probability of another not exceeding another value, which is going to be a distance involved. And epsilon is going to be the distance between the two. So then comes the probability that the distance between the two is exceeding that value epsilon as well. Okay, and it can be shown. That's not difficult. I'm preparing the reader right now, so if you want to check out the proof, you can. You will not need it for the exam, so you don't need to learn these things. Okay, I'm just basically fine if you're understanding them. Now I'm going to apply that twice. Okay, so epsilon is basically just greater than 0. I'm going to apply it twice. In context basically for xn and x, so y is becoming xn, and x will be x, so that's going to be the limit. And then I'm going to plug it in. Okay, so xn, or that was y, and the other thing is going to be just that. Okay, so x is x, and y is xn. These are the members of the sequence. Okay, that is true. Okay, I'm going to assume later on that you have convergence and probability. Now, that's number one. Number two, and that is going to be the other issue, it will have the same structure, but I'm going to reverse it, so check it out. So what I'm going to do is, I mean, this will be staying, but that doesn't indicate that y corresponds to xn, and x will correspond to x. It's actually the other way around. I mean, of course, you need to understand that if the absolute value of x and y is a certain, I mean, if this is equal to a certain thing, then that is also going to be equal to it. Okay, so the distance between x and y is the same as the distance between y and x, of course. But I'm going to reverse it this time. So this time, y is going to be x, okay, and x is going to be xn. That's coming next, okay? But that doesn't matter, okay? So that's basically how you set it up, okay? This time, y is going to be x, and x is going to be xn, okay, by the substitution. It works in both ways. Now, you can also write a here and a plus epsilon here, but I don't want to, because all that matters is the distance between the two. And the distance between the two is, let's say, epsilon. Okay, so that is a plus epsilon minus a. That's the only thing that matters. So I'm going to substitute a accordingly. A is going to be substituted by a minus epsilon. So then if a is substituted by a minus epsilon, then a plus epsilon becomes a minus epsilon plus epsilon, which is a then. Okay, so I'm going to change that as well. Because again, you don't need to, if you're confused, I understand. This is just substituting it. Reparameterization, that's the term. Okay, so the only thing that matters is the distance between these two values, which is always going to be epsilon. Okay, a plus epsilon minus a is epsilon. That's true. and a plus a minus a is going to be epsilon, and a minus in brackets, a minus epsilon is going to be also epsilon as well. Okay, so that's all that matters. All right, yes. Now, those two converge to 0 if basically you have convergence in probability. So assuming that, so we assume that the sequence converges in probability to x. Okay, now that means that these must be converging. These probabilities must converge to 0. Okay, so if you want to make it easier, then you could ignore it, although it might not be true. So that's not true, only basically the limiting of the case. And then you need to compare what you left with. Okay, you're left with basically, I mean, these are the same things. Okay, so I'm looking at the limit of that. Okay, these are equal, you see. Those expressions are equal. So that means that this is going to be the upper endpoint, and that's going to be the lower endpoint of the green expression. Okay, so we'll basically putting those together, and that was the reason why I did it. So I'm going to put in the green expression in the middle, which is the cumulative distribution function of the random variable xn at point A. I'm not sure if you noticed that one, okay, because that it is. Now, since I'm looking at the limit here, I will need to add the limit to it, because then you could take this off, okay? So when you look at the limit, then you can simply ignore those probabilities, and these are the others that you are left with, okay? So that allows me to simply just ignoring them. And this is the lower endpoint that's coming here. This is the cumulative distribution function of the limiting random variable at point A minus epsilon. And the other is going to be the cumulative distribution function of the upper endpoint, of the other end, basically, of the limiting random variable at point A plus epsilon. Okay? So this means that, as you see, okay, the distribution function of the members are squeezed in between the two. Okay? Now, if epsilon converges to 0, which is or can be done because the limiting cumulative distribution function f is a continuous one, by definition, that's going to squeeze in basically the upper, I mean, the upper and the lower endpoints are going to squeeze the function in the middle when it comes to the limit, and that's why basically you have convergence in distribution after all. So convergence in probability implies convergence in distribution, because that means that the cumulative distribution function is converging to the cumulative distribution function of the members is converging to the cumulative distribution function of the limiting random variable, which is x. That was the limit, by the way. All right, so we assume basically convergence in probability. Yes, okay, so that's basically what it was. Now, one last thing though, and then we're done. Okay, if you allow me to do it, okay, which actually have a little bit more. So mean square convergence, which is the most common one, and it's not going to be long, okay, so trust me, is also implying two things. So if you have convergence in mean to basically of order 2, let's say, so convergence in mean square, which means that this expectation will converge to 0. This implies that the expectation is converging to the expectation of the limit. Okay, so the expectation of the members will converge to the expectation of the limit as the sequence progresses, and so does the variance too. So the variance, both the expectations and the variance converge, and that's why basically mean square convergence is so common, because that makes sure that the variance, again, if the limiting is finite, that this is going to be finite as well. Okay, that's why it's so common, by the way. Okay, because that basically guarantees both. Now I'm going to show that too. It's not going to be long. Okay, what you need to know about this is the following. You only need to know basically what the variance is. The variance of a random variable is equal to the expectation of its square minus the square of its expectation. We talked about that. That's why I was introducing to it. Okay? And here I have the expectation of some square, right? Which is going to look at that one. This expression is here, right? Now, since the variance of that is going to be equal to the expectation of the square minus the square of the expectation, this is also true for that random variable here inside the expectation operator, excluding the square, of course. So that means that you end up with the variance of it plus the square of its expectation. Okay? So keep in mind, the variance of a random variable is equal to the expectation of the square minus the square of the expectation. So let's call it y in this case. And all you do is basically just rearrange that. So that means that the expectation of the square, on the other hand, which is going to be here, the expectation of the square is going to be equal to the variance, to its variance, plus the square of its expectation. Okay? That's basically just rearranging it. Okay? Since they are equal, if this is converging to 0, because that's basically the definition of mean square convergence is, then those two must converge to 0 as well. There is no way to avoid this. Why? Because this is something which is positive. Okay? That is something which is positive. Okay? And that cannot be negative either because it's a square, right? The expectation of the square. So again, both are positive. So this means that if both are positive, but they're converging to 0, then they must converge to 0 respectively also. Okay? So, and that is a convergence. So the variance converges to 0. Okay? Which means that basically, they do. And that is also converging to 0, right? Basically indicating that both the variance as well as the expectation converges. Because if this is converging to 0, so does its square root, right? Okay, that is also true. If you take away the square, this is no longer be true, but it doesn't matter. I just wanted to illustrate why both the expectations and the variances will converge respectively if you have mean square convergence. That's guaranteeing it. Okay, so basically this is it. All right, guys, that was it for today. Okay, again, that was a collection, a bunch of definitions, but I'm going to grab them sometimes here and there, and I wanted to make sure that you understand what these things are. You can bring those definitions, of course, into the exam. I will provide you with the reader to this chapter as well, and then I'm going to upload the exercises. Okay, but we have a little time starting for prep, so don't worry about it. Okay, these are the tools that I'm going to use most. Definitely, and next time we're going to start with stochastic processes, okay, and categorizations and whatnot. But yeah, I'm going to address those as well. We're going to talk about random walks, maybe, and maybe I have time to consider the Wiener process even, or the Brownian motion. I'm not sure. Okay. All right, guys, that was it for today. Have a nice evening. Take care. See you next week. Bye.